concavity and convexity criteria in the last class, and we found that for thermodynamic equilibrium or stability problem, we call thermodynamic stability as usual, and for that purpose, that is the criteria for the positive definiteness of the matrix. Is the criteria for the positive definiteness of the matrix, and for that case, we showed that our USS is positive. Okay, with that we showed that USS is positive. So, what we USS is positive, and also USS UVV minus USV square greater than 0 is the criteria, and this has been shown in perspective of Legendre transformation, because this directly you cannot show, but you can actually show this is related to HSS. We can also talk about HVV. Similarly, we have AVV and AET, right? Am I correct? And we also found that there is a criteria of the convexity and concavity. Convexity and concavity. And the convexity and concavity criteria we have shown that, for example, dou 2a by dou t square. That means ut, that is with respect to the intensive variable. Okay, this temperature and pressure, that is concavity, and with respect to the specific variable like entropy, volume, that is convexity. And this h and a, if you look at the function, h and a, h is the function of s p, am I correct? Yes. And a is the function of pv. So here, this is the intensive variable, this is the intensive variable. Each case we have only one intensive variable, and u doesn't have any intensive variable. U is the function of SV. There is no intensive variable, it's all specific variables. Okay. On the other hand, G equals to G hat TP, both are intensive variable. Both are intensive variable. Okay. And for this case, as I said, the convexity and concavity criteria. The concavity criteria occurs with respect to the intensive variable. That means I should be able to prove GTP less than 0 and GPP less than 0. Did you prove it? Answer was, the proof was very, very straightforward. If you look at the proof, that is, I defined as C12, M1, M2, which is nothing but y minus M1 x1 minus M2 x2, correct? For the G, because both are a complete Legendre transformation. There is no partial, because the function of S and B in this specific case, and S was replaced by M1, B was replaced by M2. And from here, one can get DC12, which is minus x1 dm1 minus x2 dm2, right? And it says that dou C12 by dou m1 at fixed m2 equals to minus x1. Am I correct? Yes? Similarly, one can have dou C12 by dou m2 at fixed m1 equals to minus x2. Right? You have to get relationship with respect to the dou 2 C1 to dou m1 square at fixed rate m2, or dou 2 C12 with dou m2 square with respect to m2. So we have dou 2 C12 dou m1 square fixed m2. What is that? in terms of, this is your dou C12 by dou M1, this one minus X1, right? So it will be minus dou X1 dou M1. Am I correct? Which you can write as minus dou M by dou X1 M2. And these things I am just applying. Why I am applying these things? Advantage is that inverse, if you look at the implicit function theorem, this inverse is true if there is not 4 degrees centigrade of water. If there is a 4 degrees centigrade of water, then those things should not be applied. So this thing I can directly see using as it's okay. There is no first condition, the same thing. That should be dou M1, right? Yeah. And these things we have done earlier. This derivative was there. Please look at the enthalpy. Please look at the enthalpy. This derivative was there. Minus dou M x1 by M2. What it is? What should I write? Minus dou M1 by dou x1. Y should not write in terms of Y, in terms of H. In terms of H, it is there. Dou M1 by dou x1 at fixed M2, we have proved something. In H, you should be able to tell me. You have proved last class. In H, very beginning, if you look at for the H, the dou M1 by dou x1 M2, it was proved as dou 2y by dou x1 square or something, and that is nothing but HSS. That's what I wanted to say. Minus HSS and less than 0, again it is proved that this is your GTT, am I correct? That GTT has been proved as less than 0. Similarly, if you look at GPP, that is dou 2 C12 dou M2 square M1, which is nothing but minus dou X2 by dou M2 M1, am I correct? Which is nothing but 1 by dou M2 by dou X2 at M1, and which will be coming from your Helmholtz free energy. This derivative was the Helmholtz free energy. Yes, and this is nothing but dou 2a by dou v square at fixed T. Okay, so this is greater than 0, so that means this is less than 0. So both the derivative, second derivative with respect to intensive variable has been found to be negative, less than 0, and that's it. We have established that concavity criteria holds good for the with respect to intensive variable, whereas with respect to specific variable we have the convexity criteria. Right? Clear? So now one interesting thing I would like to note here. We have done the minimization of internal energy. What will be your exercise if you talk about entropy maximization? What will be exercise if you want to talk about entropy maximization? Let's talk about entropy maximization. So thermodynamic equilibrium or thermodynamic stability means we have to talk about stable system, means to talk about energy minimum or entropy maximum. We have seen that because du equals to or du ds minus pdv plus mu dv. This you can write as ds equals 1 by t du plus p by t dv minus mu by t dm. Right? And necessary and sufficient condition. Okay, first derivative. For minimum or maxima, we know that grad f equals to 0. For minimum or maxima, later on we have to verify with the Hessian matrix. Hessian matrix has to be negative definite for this case, for maximum. Right? So grad F has to be equals to 0. So what will you get if there are two systems? First system, second system. What will you get? So remember that AC is nothing but S at U V N. So the equation will be first derivative will be dou S and dou U at fixed Vn. What is that? What will you get?
1 by T.
Pardon?
1 by T.
So 1 by T1 equals to 1 by T2. Next condition, dou S by dou V. First derivative.
P by T1. P1 by T.
P1 by T1 equals to P2 by T2. And last condition will be mu1 by T1 equals to mu2 by T2. T1 equals to T2 from here. If T1 equals to T2, then P1 equals to P2, and we are getting the same condition. What you got for the energy minimization, that has to be that condition. So these two are equivalent formulation. Either minimization of energy or the maximization of a problem. Both the same. And if both are same, doesn't matter which approach, the alternative approach you approach. Go for, you get temperature equality, pressure equality, and chemical potential equality. Okay. At this juncture, I'd like to see the second order Hessian system, and let's look at Hessian system. So we'll have specific sense. We'll have ds equals to 1 by T du plus T by T dv, right? Right? And this also says that S is S hat UV, right? Hessian matrix will be S. Who will tell me? Just one hand, please. Yes.
SUU.
SUU, SUV, SUV, SPV. Correct. So we have to find lambda's negative. Okay. So what is my that determinant? SUU minus lambda SUV, SUV, SVV minus lambda equals to 0. And we have SUU minus lambda, SVV minus lambda minus SUV square equals to 0. And we will have what? We will have lambda square minus lambda SUU plus SVV plus SUU SVV minus SUV square equals to 0. Next step, lambda equals to SUU plus SVV plus minus root T by 2. What is your T? What is your T? B square minus 4AC, man. You should not be just keeping quiet. I am just talking here 10 plus 2. If you know how to solve the quadratic equation. So what is that? D. D will be SUU SVB whole square 4 SU. What is that? 4 SUV square. 4 SUV square. Am I correct? Okay. 4 SUV square. Okay. What is the condition? You have a negative eigenvalue. First of all, this guy should be negative. Not confident. So that's what we are not responding. Somebody else is saying wrong and I have to accept. Is it not confident?
4 times SUV. One more term SUU.
You should be doing the simplification. I will stop here. I am really surprised that you guys are struggling so much to do 10 plus 2. You should not be struggling so much for doing 10 plus 2 algebraic system. Yes, I am really surprised. If you want me to do that, I can do that, but that will be too much. So this SU minus SUV square, B square minus 4AC. So Minus 4. What? Pardon? That was correct. What is the thing? I just see my situation. I am just stopping here to have the argument whether that is, I can simplify. How I can teach the higher level things. Even if I want, I cannot do that. Because I have to struggle here 10 plus 2 algebra. Correct? Only one bench. I want to see whether any other bench. Rahul, you are struggling. Man, good. Anybody can confirm? So what is that? Answer, final answer? What's the final answer? SU, SUV, whole square minus? Yes, sir. Don't buzz like that. When I'm asking so much, nobody is raising the hand. Can you please raise the hand? Anybody? That nobody is raising the hand. That's the thing. Yes, Panda. This is SU minus SVB square is correct? Yes, plus? Minus. You are saying plus, you are saying minus. Panda, please. I am just getting frustrated here because I don't know what level I am teaching. I am just struggling here to do 10 plus 2 algebraic juggler. I just stop here. Okay? I am just stopping here because we are now fighting which will be correct. Yes.
Sir, USS minus
USS. You are going to other extreme. Sir, please. Don't mislead. Anybody else? SUB plus what? Sir, if you are not sure, please.
Sir, for
Yeah, please, sir. Next.
Sir, plus 4s UV square. The last
That-
one is plus 4s UV square.
That was done earlier, no? That's what it was done, and you just wasted my time. 5 minutes. Okay? Fine. 10 plus 2 algebraic thing. It's all recorded. Okay, when I show it to the class, then they will know that how the things are in the class. Okay? What it should be? So now what's the situation here? What should be the condition for the D has to be less than 0? Not D, then lambda has to be less than 0, right? If lambda is less than 0, what should we go for? If lambda is to be less than 0, what are the conditions we think it is correct? Because your lambda is ACU plus SBB plus minus root D by 2. Okay? D has to be positive. No other way. And root D, this quantity is positive. No other way. If D is negative, then that's it. Complex quantity we don't want. We don't want to go to complex quantity. If this is positive, this has to be very much strong negative. Such that, so SUU plus SVV less than 0, first category. Correct? Is this sufficient if plus sign occurs? Of course not. Because it could be this SUU plus SVV. So what it should be? SUU plus SVV plus root D less than 0. That's the most stronger category. Okay? First category. If it is minus, what actually happens? If it is minus, then root D should be greater than equals to SEU plus SB. Am I correct? Yes or no? So first criteria, second criteria. Okay? You can get the conditions from here. You just see what are the conditions you are getting. Situation is a bit complicated. Now the thing is that, of course, you can find out SUU. What is that? Dou 2s by dou u square. What you can write? Dou u by dou s dou u. It is at fixed v. Right? What is this dou s by dou u at fixed v? 1 by 2. Okay. What will happen? Dou of 1 by t dou u. Can you determine? So This is very interesting. I don't want to do it in the class, but I will appreciate if somebody does the complete digital transformation here and submit. Maybe Rahul can try, but I don't know anybody else can try. I won't ask Devayan, so don't hide yourself. Okay? I will ask only Rahul. Okay?
So you can ask me.
No problem. I don't want to trouble. If you can give, fine. But Rahul, I can always demand, right? Yes. So I'll give you 2 weeks time. Okay? Let's see what you can do. I won't discuss in the class because I don't have much time. I have the things with that. So we'll see next time. So maybe next week sometime. Something is due, right, from your side. What is that?
Departure function
In terms of
Z.
Z. Okay. That's what I yeah. Okay. Well, when you're giving, maybe sometime this weekend. Friday. And next week you can actually try it out. This one is very interesting. So I have given the starting point. And from there we can see how the convexity and concavity criteria should be. Is there a straightforward business or something else? Things will be pretty complicated. And that will be if you can try it out, I can say that will be one of the possible second quiz exam question. So I am giving the question of the exam. This is one of the possible second quiz exam to get the concavity and convexity from the massive set. Okay, this is a massive function set. So concavity, convexity criteria for the massive function. Okay. Fine. So try it out. We just see. Rahul will be doing that. You can always get help from him, and we'll see that how we can proceed. So far we got the possible questions. One is the Helmholtz function departure, Gibbs energy departure, and we have done for the first principle, right? Departure function, and those things Rahul already derived for the equation of state like Payne Robinson SRK. This is one of the possible questions. First question. Second question is from the massive function set. Is it possible to have the convexity and concavity criteria, and what are they? This is the second possible question. So I am giving the possible questions. You know that if I say some possible questions, it's coming in the exam. We have seen the first quiz. Okay. So try it out. If you try it out, of course you learn something, and that will be helpful for your second quiz. Okay. So next will be what I am going to talk about for thermodynamic equilibrium or stability. We have seen that minimal. So this is the point where actually energy is minimum, and that's a stable point. And why you have seen minimum? Because we have just derived that Hessian matrix is positive definite, and which further confirms that energy is minimum, and the situation is thermodynamically stable. Situation is thermodynamically stable system. Thermodynamically stable system. The energy is minimum. Thermodynamically stable system, which is actually true for everything. So thermodynamically also the energy is the main role. Anything you actually move. A car is actually going in a direction, and the driver is actually putting the third gear, fourth gear going that. The driver actually releases the gears to come back. Why? With potential energy is minimum here. So everything in the system, everything in the world goes to the place where the energy is minimum, and that's what is true for thermodynamics, and that's why the situation for this is called as thermodynamical stable system. So next, T1 equal to P2, P1 equals to P2, and mu1 equals to mu2. We measure temperature, we measure pressure. Right? Chemical potential, can you measure? Answer is no. There is no meter, no equipment which measures chemical potential. Okay? Let's look at how to estimate chemical potential. Now it's very important now. At this point, when you talk about thermodynamic stable system, it is, and for the two systems, for example, you have first phase, second phase, or first system, second system. It could be two systems in the same phase, or it could be vapor liquid. Anything, two systems. Anything. It could be vapor liquid, it could be two systems, two substances, two liquid, no problem. Maybe one organic phase, one water. Okay? or it could be two solids, whatever. The same thing will apply. This is valid for any system, which can be amenable to treat thermodynamically. Which can be amenable to treat thermodynamically. Okay, so chemical potential. Again, coming back. That's the interesting episode here. How to calculate chemical potential? We have seen that. How to calculate enthalpy for a particular substance? We have to talk in terms of departure. We have shown the diagram, like TS diagram, a pH diagram, and all those things we have actually shown. So, if you look about the chemical potential departure, so any thermodynamic property can be written as departure function, which is P tending to 0 to P dou M by dou P T minus P tending to 0 to P dou M Ig by dou P at fixed T. And thermodynamic property, you can say that M equals to MTP equals to MIG TP plus, and if MIG TP is known, then you can calculate the particular property. That's the way our tables or TS diagram, pH diagram, steam table, everything is done. Right? So this could be chemical potential, right? And chemical potential can be evaluated, and we know the temperature, pressure are same, and we can evaluate the chemical potential. But now the thing is that, is it that straightforward? So you know how to do that. So what we'll be doing here, so this, what is the mu actually? Mu for the pure substance, we know that is called G, right? This minute we have already proved that, right? We have already proved the chemical potential is nothing but G, and dou G by dou P at fixed T equals to what? Dou G by dou P at fixed T. We have the things tables. Go back to customers. Dou G by dou P at fixed T equals to what? Dou G by dou P at fixed T dV. V. So mu Ig. So what actually happens? So if I want to talk about the mu Ig Tp, I want to find out this. Mu Ig Tp tending to 0, P tending to 0 to P Vig dP prime. Or we can directly write mu Tp minus mu Ig Tp equals to integral P tending to 0 P V dP prime minus P tending to 0 P Vig dP prime. I think you all agree with that. Vig is nothing but active item. V can be obtained from equation of state. Take the means in SRK, whatever. We have done it. For a system, we are talking about thermodynamic equilibrium. Two systems are there. First phase, second phase. First system, second system. They are thermodynamic equilibrium. And in that case, we know temperature and pressure. We are talking about temperature and pressure. Intensive variables, easy to measure. Good temperature was here, both the side, we just monitor pressure is same, temperature is same, job is done. In that case, if one like to evaluate P tending to 0 to P V dP prime, and this will be coming RT ln P by P tending to 0, it cannot evaluate. Because this is coming to 0 and log is gone, ln is gone. You say, okay, we'll go to the V domain. But thing is that we're talking in terms of temperature and pressure, why do extra? And in that case, again, you have to calculate the volumes and all that. There is no guarantee of the volume equality, right? There is no guarantee of the volume equality. We know only temperature and pressure. The volume we are calculating two different volumes is a big problem. Because we know that when vapor and liquid equilibrium, liquid volume is much less than the vapor volume. That solves that the vapor volume is not equal to liquid volume. That's interesting. That's very, very interesting. So we have to stick in temperature and pressure. Correct? So if you cannot measure chemical potential, what will happen? If you cannot measure chemical potential, you cannot do thermodynamic stable system, you cannot do thermodynamic equilibrium. So the question is, how to estimate mu? How to estimate mu? If you don't estimate mu, your thermodynamic equilibrium is gone. You cannot do anything on this thermodynamic equilibrium. How to estimate mu? You have given temperature and pressure, the system. The given temperature and pressure in the system. Don't talk about the vapor, because vapor will be different. If you go to the equation of the system, things are very complicated. I'm not talking about that. You can say, okay, you can convert to the V domain and do it. I won't go to the V domain, for at least for this case. How to estimate? You have to estimate. You cannot escape the system. Okay, I will say temperature pressure equal, and that shows my my system is thermodynamically stable. They are thermodynamic equilibrium. Not correct. 3 criteria. At the same time, temperature, pressure, chemical potential have to be equal for a thermodynamically stable system. So here there is a way. The good news is there is a way to estimate mu, and introduction of the concept of fugacity. Introduction to the concept of fugacity. There is a way, an introduction to the concept of fugacity. What we found that this quantity mu minus mu ig is indeterminate because of this integral. So you cannot quantify mu minus mu ig dp. So what we can see here, we can see that mu minus mu ig dp, you have the final expression p v minus rt by p dp prime, rt by p prime p prime. That's the maximum thing you can do. You end your business here. You say you cannot do anything else. Don't try to evaluate the integral. You won't get anything. So you introduce the concept of fugacity. F equals to p exponential mu minus mu ig dp by rt. What it says? If p tending to 0, mu tending to mu ig. Why? Because this integral will go to 0. Right? So this is exponential of 0 equals to 1. So F equals to P. So fugacity has the unit of pressure. It is not the exact pressure. It is not exact pressure, it is the unit of pressure. It is not exact pressure. But by fugacity, you are indirectly estimating chemical potential. Okay? By fugacity, you are indirectly estimating the pressure. And this is defined as fugacity. Now we can see why fugacity is required. Fugacity is required to replace chemical potential. Fugacity is required to replace the chemical. So now you can see entire departure of chemical potential can be expressed in terms of fugacity. So fugacity is directly related to the departure of chemical potential. And you see that if P tending to 0, mu is equivalent to mu ig. Okay? And we also define fugacity coefficient. Fugacity coefficient, which is phi, which is F by P. Okay? And which is, we can write this as exponential 1 by RT, P tending to 0 to P, V minus RT by P prime dP prime. Understood this one? Fugacity coefficient? Yes. Because mu minus mu I, see 1 by RT is coming here, and mu minus mu I is the departure formula, V minus RT by P prime dP prime. So this is the formula for the fugacity coefficient. Okay? When you define the fugacity coefficient, you don't need this part. You only need this one. F by P. Phi equals to F by P. Okay? Phi equals to, and I will show you that for how to calculate fugacity based on various equation of state. I will show you how to calculate the fugacity for various equation of state, and also this alternating expression of this I can also write wants to write the departure of chemical potential, which is RT ln coil equals to RT ln F by P, P tending to 0 to P, B minus RT by P prime. Now you can see that this is your mu minus mu I GTP prime, right? The departure of chemical potential is nothing but RT ln phi or RT ln F by P. So many things we have learned. Now, since we have got fugacity coefficient, what will be your modified condition of thermodynamic stable system? We have temperature equality, we have pressure equality. Now we want to replace the chemical potential equality by the fugacity. Okay? So what will be that replacement? We know mu1 equals to mu2. Right? mu1 equals to mu2. And which is nothing but mu ig. Mu is nothing but mu ig plus some other term, right? Mu ig Tp. That means mu equals to mu ig Tp plus RT ln phi. Yes, or RT ln F by P. So from here it is written that mu equals to mu ig mu Tp. We should write the function Tp is RT ln F by P. This is also phi. Yes. 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 Okay. So mu1 should replace mu ig T1 P1. You should write very carefully. mu1 is nothing but mu ig T1 P1 first system plus RT ln what? One hand please. RT ln what? RT ln what? I am very surprised. Some trivial things on the board you cannot even read out. Just I want the hand. I don't want any buzzing. Not Rahul. Yes, Panda. F1 by P1. Simple thing I am asking. F1 by P1 equals to right hand side. Who can volunteer? Right hand side. Any hand please? Right hand side. Any hand please? Right hand side. Who can volunteer? Right hand side. Right hand side to what? Any hands? Yes sir. Mu ig T2 P2 plus it should be RT1 RT2 ln F2 by P2. Mu ig T1 P1 mu T2 P T1 and P1 same T2 P2. So this term will get cancelled because T1 equals to T2, P1 equals to P2. This T1, T2 will be cancelled, R will be getting cancelled, P1 will be getting cancelled with P2, and we find F1 equals to F2. So the third criteria, which is replacement of from mu1 mu2, which is nothing but F1 Tp. So, and same thing, we can also write third criteria as F1 Tp equals to F2 Tp, or we can write fugacity coefficient Tp equals to phi T2 Tp. So many things we have done. Okay, so temperature equality, pressure equality, fugacity equality, or fugacity coefficient equality, or fugacity coefficient equality, or fugacity coefficient equality. Okay, so we know it. And how to estimate fugacity? We know that fugacity and pressure they are related. Okay, and for ideal system, fugacity is equal to pressure. So fugacity has the pressure in it. It is not exactly pressure. Okay, it is not exactly pressure. And it is possible to estimate fugacity based on the equation of state. We'll come later. But now let's go to the equation of state and see something fundamental in the equilibrium part. So long back I talked about the calculation of saturation pressure. I talked about calculation of saturation pressure. So if you look at PV diagram. This is your physics, right? This is the physics, mathematician. Okay? So physicist will say this same system, mathematician will say no, I cannot give any function which has two discontinuity. Any function will be continuous function, and mathematician will say that my function is like that. And finally physicist and mathematician both are correct, because if you integrate even P dV, that means if you are, this is the initial point and final point. So first point, second point, this is your third point, and this is your fourth point. Okay? So if you follow 1, 2, this path, say 2 prime and 3 prime, 1, 2, 2 prime, 3 prime, 4, or 1, 2, 3, 4, both should be same, right? Same path. That means what I said earlier, these two areas will be same. If these two areas are same, then only you can say this mathematician and physicist are same. Otherwise they are different. So, and the thing is that this is liquid part and this is vapor part. That means here and there equilibrium. Now we know the condition of equilibrium. What are the condition of equilibrium? T at this point, at saturation point, at saturation, this is the saturation point, we have T liquid equals to T vapor, P liquid equals to P vapor, F liquid equals to F vapor, or phi liquid equals to phi vapor. Right? For vapor liquid equilibrium. For vapor liquid equilibrium. We also proved for this branch, 2 prime, 3 prime branch, dou P by dou V, T which is greater than 0, which is unstable, which is not correct, it is unstable, which is thermodynamically unstable. Dou P by dou V at temperature greater than 0. This regime, dou P by dou V less than 0. This regime, dou P by dou V less than 0. But this regime is entirely greater than 0, which is not thermodynamically correct. So mathematician is giving something wrong, but finally they are, all the results will be same. And also I told earlier, when you are doing TS diagram and TP diagram and pH diagram and TS diagram, I told you to calculate the saturation pressure. Okay? And thing is that when you are getting the data, you are getting data like this. So one can draw like this, or somebody can draw like this. How we draw? Because you can say, I will show you from this diagram. This line could be here. This line could be here. Right? This is called P minimum. This is called P max. This is P minimum, P maximum. Beyond P minimum, you will get only one solution. Beyond P max, you will get one solution. Otherwise, up to this, you will be getting 3 solutions. 1 year, 1 year, 1 year, 1 year, 1 year, 1 year. How to see that line is correct? Which line will be picking up? You cannot say this is my saturation pressure, because this area and this area are not same, and you will be getting wrong result. This is not saturation pressure. Even this doesn't exist, this point. This means it is different. Okay? How to fix up this line? How to fix up this line? That's why you have to calculate. You have to draw your pH diagram, PS diagram, or this diagram. You have to draw this diagram. Forget about your pH diagram or PS diagram. How to draw this diagram even? Which line? Because if you do Carnot's method, when you solve your Carnot's method, you will be getting this kind of solution. And some solution here. Like this. 3 solutions. Beyond here, you get 1. Beyond some P max, you will get 1. Otherwise, you get 3 solutions. How will you join? Like this, or you don't know how to. The thing is that you have to, either you can calculate P max or P min. That's very difficult to calculate. Because if you go much further, you will miss it. Some particular point P max and P min occur. And you have to join such that, and this line is also important. Which line this is? Shall I pick up this line? Or shall I pick up this line? Or shall I pick up this line? How to get this line? And this line will give you P sat. This line will give you P sat. So now the question is, it is very difficult to draw PV diagram. Because once you fix up this, then this will go. You have your actual physics. To predict the actual physics, it is not that straightforward. It is very difficult. Okay, so let's first prove that these two are equal here. Then we'll go to calculate how to calculate the saturation pressure. Okay, so our objective is to go to the situation where the two areas are equal. This is the point, I am saying this is the point I, and this is the point I prime. Okay? At point I, this point X is in vapor phase. Point I prime is in liquid phase. Point I in vapor phase, point I prime in liquid phase. Right? At point I in liquid. So what will happen for the point I? If I write in terms of fugacity, formula, what formula I will actually use? RT ln FB by PV equals to you have the formula with you. You have the formula with you, is equal to some integral, right? Is equal to some integral. What is that? What is that? This Pi, you can say FB Pi equals to P integral P tending to 0 to Pi, then V G, not V minus, you just don't do it, you know, if you do just like that, you are just doing some clerical work. It is VG, right, the vapor phase. Unless why should I write this? I could have just like RT by then go. Why I am shouting, why I am wasting my time, wasting my energy, rather. Okay, minus RT correct? At point I prime, RT ln FL by Pi prime equals to so my basic equation is RT ln F by P. I am just writing the equation for you, which is V minus RT by P prime dP prime. Equation number A. This is equation number B. If you say equation number C, I will finish the class. Equation number B. RT ln P by prime. To come to this, remember that your basis is P tending to 0 integral. So it has to come to I. Then point number 3 prime. Then come here straight. You have to go by equation of state. And then come here. I prime, right? So can you tell me the steps? He has to go to first 4 point, 4 to 3 prime, 3 prime to 2 prime, 2 prime to 2 or I prime. What is that? How many integrals will be there? How many integrals? 4 integrals. You are correct. 4 integrals. Now can you tell me what are the 4 integrals? What are the 4 integrals? Okay, I will stop here. I think next class you think about it and we will start in the next class. Thank you.